Yes, yes, we
Okay,
speak.
good, perfect. So then we can begin. So what we will do today, I'll speak about Woodwork for Inventor capabilities, what we can do starting from a design concept and ending up with the manufacturing data generation. As a model for this example, we will take something like sales mall furniture, let's name it like so. As you can see, it's shown on the left side. It's like hand-drawn sketch. That can be like the task for a designer to refine. And our goal is to make it detailed. And the way how we will do this is using skeleton design workflow. Now we will see how it will help you to design such quite complex model using some simple primitive steps. And everything starts from the skeleton. And as you can see on the left side, it's like very basic shape of the furniture. So we can see that it combined of multiple geometrical items, but all that stuff is done on a simple single part. So we're using multi-body functionality of Autodesk Inventor. It's parametrically driven, so you can change some values and see how it will react to the changes to check your design ideas. Once it's done, you can split this single model into the blocks. Each of those blocks derives shape and position, and you can just refine each of those blocks later when needed. So for instance, we can take one of those blocks to define how the metal parts will look like in it. We can apply frame members using frame generator of Inventor. We can use sheet metal parts. We can use some custom-made metal stuff. And all that adapts to the changes of a concept. Of course, beside the metal part, we can also work with some wood. So let's say that that's how our finalized metal part looks like. And we can go for the wood part. As a reference, again, we can use the same block. And on the same block basis, we can apply different panels made of different materials in different shapes. We can also use library items. And after all, when we will finish that part, it will perfectly match with the metal components. And again, it adapts to the changes. So if you change something on a concept level, of course, it will react to those changes. So now let's take a look how it happens in the real case. So initial data can be various. For instance, we can have a sketch on a napkin, as I showed you. We can have some more detailed information made by a designer or architect. So in this case, it can be AutoCAD drawings. So you can also have some 3D drawings maybe, or we can use some mixed data. Maybe some general shape can be done in AutoCAD, some refinements on napkins and so on, maybe some PDFs, and we can blend them together in order to start our work. So let's see what will happen in case we have nothing, if we have only sketch on a napkin. So in this case, we can use parametrical design in Inventor environment to build our initial sketch. So what I'm going to do, I will use a single part as a skeleton, and here I define the width and depth and height of this unit using very primitive steps. As you may see, everything I do, I define through our parameters, and then I can use simple Inventor features like sketches, chamfers, and so on, in order to build something which reminds the final model by the shape. It's not a final model in any means, but we can understand how it will look like, what the shape will be, what is the size, what is the critical dimensions, and so on. Having that in mind, we can think about if our design decisions were right, and if needed, we can easily change it. Because this initial design can take, let's say, maybe 2 or 5 minutes. Yeah, so you can just quickly build this, say, a 3D sketch, 3D napkin sketch on a 3D, okay, and in Inventor, sorry, and then you can see if your design intent really works as you expect. Okay, and as you can see, I'm using multi-body design methodology, which means that when I do extrusion operation, I set this as a new solid body, and this will allow me to have better control because I can split top portion, which is like a glass frame, from the bottom portion, which is like a panel component. Okay, so as you can see, after all, We spent just maybe 3 minutes or so, and that's how our concept is looking. So that's one of the ways how we can get initial data, which we treat as a skeleton. The other more interesting way is when you have something built in another CAD systems, maybe in 3D or in 2D. Like for instance, often we are getting some AutoCAD data, but as you may see, this initial data is not very rich. Yeah, it's just some critical data, general shape and dimensions. But nonetheless, we can use it. So you can see I imported this geometry from an AutoCAD drawing, and then you can just simply define the blocks. As we saw previously, I can do this with just a regular design in Inventor, but why not to use existing AutoCAD drawing, if it's possible. Okay, so we can have multiple solids, as you may see. Each of those represent future piece of the furniture. Later on, if you see that this design works, we can apply some more details, check another design steps and see if they combine together in the right way. And that's it. Now let's see what will happen in case if the designer or architect which sent us this initial data changed the idea slightly. Maybe he got some notes from the customer. Maybe there's a space to make this sale point bigger, so we can increase the size symmetrically in original AutoCAD file, or maybe just update the AutoCAD file we got from a designer. As you can see, our 3D model built on this ground automatically updates to adjust to the changes, which is a very significant step. So later on, we can split the model in blocks to make them defined. Yeah, so we can use regular work planes. If you see that this concept is correct, I can use work planes as a split tool in order to define the shape of each of those blocks. Like in real furniture, we will combine that from multiple pieces. So actually, now we have a single one. So what we can do, we can use some split functionality. Using the work planes, I can actually refine my model. Now we have multiple solid bodies. Each of those can be made and saved as a separate part in Inventor. This significantly simplifies the design workflow, because I don't need to care about entire model. What I do, I can focus on a single block in order to refine it to needed grade. Okay, so now as you can see, we have a set of blocks, and I can take one of them, like this one, and at each moment of time, it have a relation with the parent model, with this original skeleton, because it's derived. So if needed, I can include some additional geometry, maybe some sketches, maybe some parameters, working geometry, work points, work planes, whatever else I need. And then I can do something using this information. So I can always go back in my skeleton, add some missing, let's say, points, and then include this information in my design. For instance, I can use a shape of the frame in front, which will protect from accidental damage. The glass panel in the front will be protected by the frame, but you need to know the shape of it. Yeah? So that's why I can include the shape in my original skeleton, as we name it, and then include the shape of this skeleton in each of the blocks to use it for refinement. And of course, all that reacts to the changes. Now let's take a look at the materials. So say that we have used one of the blocks, and then let's see how the material will work on it. Okay, so to make some material assignment, first we need to define the shape of some panels or some metal parts. It actually depends on what we are doing. So in this case, we are dealing with the panels, so that's why you can use a Woodwork for Inventor feature, which allows me to apply the panels with ease. So what I'm going to do, I'm selecting the surface, which will represent the color position, define the thickness of the panel, and all the rest is done by Woodwork. So I'm just selecting the surface, and it means that here we have a panel. Then I define the position. Does it goes on top of the surface or it goes inside? And then I set the thickness in such a way I can easily define needed items. Once it's done, I can make a new assembly of wooden pieces. Now when I have an assembly, when I have final parts, I can define the materials. So in this case, material matters since we apply different calculation methods. For instance, if I'm using a board material, I need to know how many square meters of this material I need to use. If I have a profile, I need to measure its length, right? So I can see all that data immediately in Woodwork BOM. We can see that we have different sizes of part and a workpiece depending on the adjustments I made. On this step, I can also assign the edge banding, which also changes the size of a workpiece. So if you take a look again, you can see that there is some difference, 2 mils difference between the final part and the assembly, and the workpiece, because of the edge banding thickness. Okay, so we can use it in 2 ways. We can apply the final thickness on the model and then use internal position of the edge banding, or vice versa, we can apply it on the top. Moreover, we can also set the grain direction, because according to the grain direction, the size of the workpiece will be changed. So in this case, the grain goes along the longest edge by default, but I can change the grain orientation if needed. And on top of that, I also applied some extra oversize, okay, for technological purposes. So if you take a look at the BOM again, now you can compare the length value. As you can see that it's way bigger than it was before, since I use 10 mils from both sides as an extra oversized value. So basically, you are getting what you see on the model, which is very convenient. Now I set the grain direction along this edge, okay? And since the grain is significantly rotated, you can see that in this case, I need to have way bigger workpiece than it was before, okay? Or smaller, it actually depends on the actual adjustment. So we have a cover workpiece here, and we have a edge banding direction. We can also apply some multi-layer boards if needed to get desired thickness. So in this case, I can use a multi-layer board construction, which allows me to define how many layers I will have to reach this final thickness. So here I have a value of a thickness, and I don't need to have separate layers designed in Inventor. What I'm going to do, I just say what is the name, the code of the material, okay, and what it will be made of. So I can insert new layer, which will be, say, some laminate. So I can find some veneer or laminate. Okay, and this will be on the top. And you can see preview on the left, which will indicate what will be the structure of your multi-layer board. And on the BIM, you'll get all those layers shown separately. On the modeling side, you don't need to do this. What you need to do is just decide what layers will be applied in your model. And once you're happy with the layout, you can just say apply, and that's it. And on the top, you'll see that the top part is made of multiple layers, which in this case is 4 layers, since we defined the veneer, 2 MDFs, and another veneer. So each of those layers will be calculated automatically according to the size of your desktop, which is very nice in comparison to what you need to do to get these values in vanilla Inventor. Because in Inventor, you should design them like a separate assembly, which is like routine work, which leads to some mistakes and slows down the workflow. Okay, now let's take a look what we can do with the metal part of this furniture unit. Again, we can use a skeleton design workflow. In this case, I'll use the same volume, the same block as a reference, But in this case, I'm defining the space for a frame. So first of all, I'll just define where this frame would be. So we can say that I'll have two extrusions between left and right sides, and later on I will use this a place for frame members. Okay. So here I can quickly add some more sketches, which will be used as a reference. It's not a rocket science, so that's why I will speed up this process a little bit. Okay, so let's say that we have two references and I can make a new assembly. Okay, and since this moment, because I'm on assembly now, I can use a frame generator of Inventor in order to place the frame members. Okay, so we can go to the design section of Inventor and then choose a frame member, which will fit our design criteria and indicate where it will be resided in the model. Yeah, so we can use different standards. Then we pick the family of the profile, define the size, the material, in this case it will be steel. Okay, and tweak the profile cross section. Okay, once it's correct, we can just rotate the profile to meet the design intent. And in this case, this volume, this general volume we built in the previous step, works very well since we know where the frame member should fit. Okay, so it doesn't go somewhere in the air. It perfectly matches the needed position since we have those reference solids. And later on, we can make a rectangular frame all around, which will work as a support to hold the weight of the unit. Okay, and basically we do the same on the opposite side. Okay, then I can use a miter tool to join the frame members in the right way. So in this case, we will have a cut by 45 degrees, like so. Or I can use trim extend function of Inventor to define where the frame should stop. So as you can see, we can use all the functionality of Inventor without any limitations. So after all, after a few additional steps, this is how our model is looking. And now we can use some hardware, some fasteners or some supports from the library. And in this case, as you can see, we can use some metal supports. And there is a Woodwork functionality, which is a hardware touch command. And this command allows you to place the hardware on the right position by simply indicating what is the reference geometry. So you can say there is the support surface, there is the side surface, and there is the axis, and that's it. So we have all those supports on the right position in a few clicks. Moreover, the hardware can also generate holes. As you can see, when I place the hardware, I use some sculpt command, and that's it. So we have holes on the right spot. And if we move the reference plane, the hardware moves accordingly, and the holes also changes their position, which is very nice in my opinion. And as you can see, when we place the hardware, we get holes automatically, so you will never miss the hole position and the hardware position. Yeah? So they will always coincide on both joint items, which is very, very nice. And in such a way, you get rid of some mistakes. So now in a similar manner, we can apply some other brackets or other hardware members, which will fix the structure in place. Okay. And there is no limitation on how you use the tool. It means that you can use patterns, you can use regular constraints, you can use Woodwork functionality, and it will work fine. So in this case, we just multiply the items like so, and we are ready to mount the front panels and join the metal frame with the wooden parts we designed in the previous step. Like a side effect, since we use some frames, we can also use a frame analysis of Inventor to verify if our design is working fine. So in this case, we are caring mostly about the deformation, so we can apply some loads to see how the frame will deform when we apply some lighting mechanisms on the top. So we know the weight of the lighting system items, we know their position, so we can apply the loads and see if the frame deforms in some certain limit. So in this case, there is no problems. The frame is quite robust and the deformation is not big enough to cause some issues. So frame analysis show that everything is working fine. And we can move to the next step, which will be the usage of the iBox. So in most cases, when we use some structure, this structure contains some standard items like the drawers or maybe some cases or the cabinets and so on. So we can define them in advance and later on using our designs. Those components can be smart. And by saying that, I mean that they can have some iLogic rules which will define how this component behaves when you change the depth or height of the item. So in this example, the length of the slider of a drawer automatically switch to the next value when the depth changes. So what we're going to do in this case, we will define the prototype of the cabinet. Okay, so we already have the metal structure, we have some panels, but there is no cabinet, so we want to have a cabinet and we want to have the drawers in that cabinet. Okay, that is our design idea. So what we're going to do, we will go back to the block level, and here we can apply some additional geometry in order to define the position and size of the block. So somewhere here we have a block. Okay. So I can just define the position of a block, which will be just a simple box. So I can project reference geometry, finish the sketch, make an extrusion, and define critical distance. So that's the new block. Now I can make it like a reference. Okay. So we just inserted this newly created block in our wooden design. And here we can use iBox placement mechanism, which allows me to define the position of an item by simply showing the front, the top, and the side. As you can see, while I'm doing this, the model changes its size and the position as well. So now we can open this standard cabinet and then add some extra bits of information, because this cabinet doesn't fit my design criteria. So maybe I need to have some spacer in between. So we can always do this. You can always add some extra details to the generalized model. So now I can use blend between the Inventor and Woodwork functions to define a right position and size of the panels. Okay, so in this case I'm using trim function of Woodwork, which allows me to cut the panels to the right size by just showing where is the limiting factors. As you can see, in such a way I just made a like a shelf in the middle. Okay, and I can make another side panel for a more robust structure. Okay, and now I can define some of the geometry to be visible. Okay, the skeleton is not needed for me. So now I can define the size of a drawers. Okay, and I can visually check how those drawers are looking like. And maybe have some identical drawers, some unique drawers by their size. So I can easily do this by just defining a sketch on the front. If needed, I can apply reference parameters, know what is the distance, okay, what the spacing should be. And then you can build the body of a single unique drawer. So we built one smaller drawer on the top and one bigger drawer on the bottom. Now we're going to use this as a reference to make our iBox placement procedure. So I can define the top, the front, and the side of the top drawer. And since we have another size of the bottom, which is like common case, we can place another instance and define its position. Okay, as you can see, we have two different drawers in a matter of minutes. Okay, so now I'm going to use a pattern since I need to have more than one drawer, so I can define the direction in which the pattern goes. And that's it. So we have those drawers on the place. And as you notice, those drawers already contains materials and they already contains the hardware, which is very important. So now we can blend them together. We can just place the wooden part and the metal part together in a new assembly of a second block. Like in this case, we're using this one as an example. And on top of that, I can apply mounting hardware, which will join the metal frame with a wooden part. And maybe I need to apply some extra items, like in this case, the frame, the protection frame on the front. So as you can see, in such a way, we can work in a very elegant way on each moment of a time. You're working with a small block. You don't need to waste a lot of time of thinking how they will combine and so on, because you can treat each of those blocks standalone. Okay, so now let's take a look what will happen in case if we need to do some modifications. Yeah? And since this model was done as a parametrically driven, and the design modification is quite easy operation. Okay, so what we're going to do, we will analyze interference in order to find if there is no issues in our design concept. So we can ask to check the collisions between the frame and the wooden part. And in order to find something, there is a collision that needs to be resolved. Okay. So we can see clearly that there is something which goes in a wrong way. So I can open the structure and see what causes the issue. And it turns out that there is the metal bracket which doesn't fit in a proper way. So we can take some measures in order to fix that issue. What we will do, it actually depends on the design problem. So maybe we will change the frame position, maybe we will change the position of the back panel. So in this case, probably easier way will be to change the wooden part, because to work with panels, it's always easier than to do something on a metal. Okay, so we change the skeleton concept, then we refresh the changes. And that's it. So now there is no intersections. We can visually check if there is a clear area, if there is needed clearance between the items. And if you see that there is spacing, there's the support on the bottom, which not makes any sense in this case. So seeing on the top portion, there is no intersection anymore. We can see what will happen. Also, we can do the changes not on a block level, but on the final model as well. Maybe the total height of each of those blocks need to be increased. So we can change this height and just update the changes and see what will happen in this case. Okay. As you can see, when I update the situation, the model just adjusted to a new situation without any issues whatsoever. So in such a way, on one hand, you can have like very robust changes, and on the other hand, you have very complex model. Now let's take a look at the BOM. because this is the point when we already finished the model. Let's imagine that in such a way we already made another blocks and see what we can reach from the model at this point. So BOM generation is a very routine procedure if you do this manually. So let's take a look at the BOM items of Autodesk Inventor. If you take a look at a single part, what Inventor can tell about that, it's like the name, code, part number, maybe the mass, and so on. But this part in the woodworking industry is something more than that, because for the woodwork for Inventor, we know like the combination of materials inside of this part. Say that we have a laminate on the top, we have core material, laminate on the bottom, we have some edge bandings, and the size of each of those layers is different because we apply different oversizes, we set the grain direction, and so on and so forth. So this is like an extra layer of material Woodwork for Inventor deals of. So now let's see how it actually happens in a real case. Okay, so this is our final block, and we can go for the BOM and see what result does it gives you. Okay, so we have all the panels, all the frame members, but moreover, now we can export this data in Excel file, and different companies have their own vision of how this final data should look like. So we're using something we call a template. There's like a specially formed Excel file with a set of keywords, with a set of parameters, and we can change their layout. Yeah, we can change their position, we can change their amount, we can change the parameters on their own. And on top of that, we can also apply Excel scripts, formulas, and so on. So basically, with the final data, we can do a lot of good stuff. Okay. So let's say that we have set the template. We can use different templates for the same unit. And this is how our report is looking. And once again, this is one of the many ways of how your final report can look like. So we have a product structure, which shows you like a general information. We have a composite part, multi-layer part, and so on. So our idea was to split the data by needs of individuals, different people who works on the different stages of a manufacturing. Yeah? For instance, for a man who cuts the workpieces, we don't need to show the hardware. Yeah, and in the material summary, maybe we need to just know the totals of materials, yeah, without caring about each of the parts standalone. Yeah, so keeping that idea in mind, we made our BOM generator, which is a great tool to save a lot of time for your manufacturing data preparation. Yeah, so if you change the model, if you change the materials, oversizes, grain direction, and so on, you can just easily generate new report in order to match the changes of your design. And here you can see a few examples of the BM of Woodwork. So you can see that they can look completely differently from what we saw. Yeah, we can have QR, barcodes, we can have pictures, we can have a different kind of grouping, we can produce the specially formed Excel file for the ERP systems, we can apply some scripts to do some custom grouping, and so on. So the same data can look completely differently depending on your needs. So we can have virtually limitless amount of the restructurization options. Now let's speak about the drawings, because it's not enough to only have a BOM. In most cases, we need to have a drawings to indicate how the structure will look like. You can also think about how much time you will spend on defining the drawings manually. So you need to set each part position on a drawing manually. So even this not a big block, single block, can take a lot of time for defining the drawings for it. So Woodwork have a tool which is called Autoplot. And what it does, it allows you to automatically generate drawings according to some rules. So basically in Inventor, you have a lot of things to do with the styles. You can define a lot of style options. And on top of that, in Woodwork, we can also define how those automated drawings will look like. Yeah, so we can have a specially formed drawing layouts with different view styles. We can use Excel tables with Woodwork information. We can have a different whole table representation, different markups of the cover. We can have dimensions placed automatically. We can have some labeling symbols defined by a customer, and you can have different formats to exporting the drawings. Yes, so there's a lot of options that you can adjust. On top of standard options, you can adjust in Inventor. And when you're happy with the results, you can save this template file and then use it in the auto-plot functionality. Yeah, so we can just start the auto-plot and see what result will be generated. The more components you have in a drawing, the bigger advantage you're getting because of the time saving. So now we can open one of those drawings, and what you can see is like a part. We have different colors for edge banding. We have a hole table, can be the coordinates of the holes. We have a grain direction symbol, shows you how the grain goes. There is like edge banding legend, and so on and so forth. So we can basically have all the information you need for a production of this part automatically shown on a drawing. Of course, on top of that, you can also apply some assembly structure information. Maybe you want to see the hardware, maybe you want to see block composition and so on. So you can do this. And of course, since we are producing drawings in native Inventor environment, if you need to have any extra annotations of Inventor, there is no issues of doing those annotations on top of drawings generated automatically in Woodwork. And now let's speak about the CNC. Okay, so some of our customers get rid of the drawings of a part since they can do the CNC automatically from the Woodwork level. And why you need to do drawings? In most cases, you're doing those drawings for a CNC. So if you can use a CNC in an automated way, then maybe you don't need to have a drawings for the parts. Okay, so what we can do, first of all, we can define our virtual machine by saying what tools do we have and how. Okay, I hope you can hear me now. Okay, so we can define how those tools are working, yeah, what they do. So what is the length of the tool, what is the orientation, and we have four kinds of the tools. We have blind and through drill bits, we have annealing tools and saw blades. So they do all the work. Okay, and once we have a definition of the machine, we can define the spindles. Yeah? Once we have the definition of the tools, we can define the spindles, which in a few words defines the orientation of the tool in some certain spindle in a machine. Okay, so once we have all that information defined, then the tooling can be applied. Okay, the tooling can be applied in different ways. So I can do this in the manual way, or I can apply a completely automated workflow. So in this case, I can additionally define some rules you will be guided by. So what is the critical factors to apply one tooling operation or another? What is the based clamping position and so on? And once it's done, I can automatically generate the program by a single press of a button. So I can choose the machine, and Woodwork knows what is the tools available in this machine and how to do the operations. And then you can see that we have operations in the browser. So if needed, you can do fine-tuning. You can change some parameters, yeah, and do some adjustment, and that's how it works. So we just click on auto tooling, and basically we get all the information. So we have a simulator tool that allows you to simulate the tooling and see how it performs, if any changes is needed or no, and then you can apply the generation of a program, like so. And in this case, there's like a Woodwork bus processor was used in this scenario, so you can see that we have a program for a Woodwork machine. Okay. So on top of that, if there's some complex case, we can apply the tooling in a manual way. Yeah, so we have a lot of options to define what we have. Is it a workpiece or is it a part? Define the base point. We have 8 options available for one side and for another. We can say what we're doing with the workpiece. Is it with oversize or without? Okay, and once we set the base point, then we can do some operations. So as you can see, this can be done completely in automated way, but if you like, you can do some manual adjustment. You can be precise, yeah, and say that you want to do this tooling with that option set or another thing. Okay, so we can see that it makes some cut operations. And then we can apply some pocket. And what is the strong point of Woodwork? As you can see, I need to mark each point standalone. Even if I do this in a manual way, yeah, so it can collect the data for operation automatically. So basically, you can even apply Woodwork technologies on non-Woodwork made models. Yeah. What you need to have a material set for the part, and that's it. So you can just, we don't care how you made a hole, using extrusion, using hole tool, or using hardware. In any case, it will do the job. And of course, on the top level, on the assembly level, we can say, please do the CNC tooling automatically. As you can see, it made all those operations for the panels. Yeah, so you can just check how the panel CNC operation is looking, and if we're happy with the results, then we can just generate the programs for all the panels in a single click of the button. So I can use output. So basically, you need to press 2 buttons, auto and output for assembly, and that's it. And you get a bunch of files. The information of those files depends on the bus processor used. So in this case, on the Woodwork machine, we have the base point, the clamping, we have all the tools shown, all the tool paths shown, grain direction, edge banding is shown. So on the machine, for the operator, for the CNC operator, it's very clear of what will happen after all the operations. Yeah? So that's what we can do. We can get rid of the drawings of the parts, because on Woodwork we can automatically generate the CNC on assembly level using some rules and some guides built in the system. Now a few words about the vault. Basically, the idea here is that in Woodwork we have some additional information, yes, like edge banding, maybe veneers or laminates, the size of the part, the size of the workpiece, and we can send all this information in a vault, in item master, and build all those items. Yeah, so we can just rebuild the structure automatically in vault. Okay, so now let me just show you the workflow once again to just make things clear. We started from a simple skeleton concept, then I split this concept to the blocks. Then I took each of the blocks separately, and then I split the metal part from the wooden part and did some refinement. I set the materials, the oversizes, grain direction for the wooden part, just set the materials for the metal frame members. Also, I applied some ironmongery, all the hardware. I need to just fix the things together. And after all, once we have the metal structure done, I can apply FEA analysis, final element analysis, to check if the deformation are in a safe zone. And on the wooden side, I place some eye boxes, some predefined prototypes, which is guided by some rules, by just simply showing where's the reference, where's the front, where's the top, where's the side. Then I blend them together. I just applied the metal parts together with the wooden parts. I apply some joining hardware between the metal and the wood, and that's how this final block burned. So in such a way, we finalized our model, and since this moment, when we have a finalized 3D parametrically driven skeleton-based model, we can use it as a source of information for the production. So what we can do, we can get the bill of materials, the drawings, CNC programs, and the nesting layouts automatically based on a model. And all this data can be sent to the PDM. Of course, we have in mind Autodesk Vault PDM system. And all the data you need for the production will be referenced with the model and placed in a single place available for all the participants on the design workflow. And now let me finalize my explanation with a few examples. So we can work on a different scale. There's like some jewelry kiosk you saw during the demo, but we can work on a simple layer model like you can see here. There is no limitation on the geometry, on the complexity. So we can say that the creativity is your limit. Yes, so basically we can even do some boat cabins, which is also skeleton driven, and the furniture can adjust to the shape of the yacht. Yeah, we can do some classic or modern furniture like this reception and so on. Also, we can blend the metal, wood, some frames, some custom parts, some mechanisms, and so on. Like in this cosmetic stand, and the shape can be very various. So in this case, we have some frame inside, timber frame inside, and then there is some nice veneer on top of that. So that's basically all the information I'd like to share with you. And maybe you have some questions. Okay, so as I can hear, there's no questions. So then I can just thank you once again for your time.
Okay, Igor, thank you very much for the presentation. I think we can end this session.
Okay, thank you guys.